So let's get into some special applications of ratio and proportion. One of the most common applications of ratio and proportion is that of scale drawings. So, when we're talking about scale drawings, these are drawings that have their roots in reality, but we're just making either a smaller or a larger replica, so to speak, of what we're talking about. So, some really common scale drawings that we see is when we are talking about architecture and we are uh, putting together like some drawings to figure out how we're going to say build a deck. Okay. So say, you've got a deck that you want to have built on your house. And when we're looking at this, maybe your architect is going to come up and they're going to draw out this scale drawing of your deck. And hopefully, your architect is going to draw your deck a lot better than what I am. So, the architect tells you, well, this scale drawing is, say, 3.5 inches wide, and it is 10 and 7/8 inches long. And we know that you want your actual deck to be 14 feet wide. Okay. Well, we might look at this and think, well, can we compare these two different things? I mean, we have inches, we have feet. And on one hand, and when we get into chapter 2 about measurements, we're going to look at converting measurements. But right now, we can create the ratio of length to width. And when we create this ratio, we really don't need to do any converting of measurements or anything. We can just go with what we've got. So if we have 3.5 inches, um, yeah, we'll just say that that's the length. And our drawing is 10 and 7/8 inches wide. We want that ratio to be the same as the ratio of the actual length and the actual width. Okay. So now, like we learned before, what we want to do here is we want to cross multiply and then divide. So we're going to do 14 times 3.5. And that gives us that, draw it over here, that 10 and 7/8 times the length is going to be equal to 49. So we can take our calculators and divide both sides by 10 and 7/8. And if you need help doing this with your calculator, just let me know and let me know what kind of calculator you have, and I'll be happy to help you know how to input this. So when we put this into our calculator, we have 49 divided by 10 and 7/8. And that gives us that the actual length of our uh, deck is going to be 4.5 feet long. So this is just an example of how we might use ratio and proportion in some applications. So another place that we might see um, where we might see special proportions is when we're talking about similar figures. Okay, and when we're talking about similar figures, the ratios of the corresponding sides mm, cannot spell are proportional. Okay, so that's a lot of fancy talk. What does that actually mean? Well, what that means is we can consider that if we let's say that we have two triangles and we have this triangle, okay, and then we have this triangle, and we are told, let's label this like A, B, C, and say D, E, F. Okay. So, because we are told that these two triangles are similar, it's the little mathematical symbol for similar, then we can say that, say, the ratio of A over B is the same as the ratio of D over E. So, if you notice, you can kind of see like where we're getting these from. So, A and D are these bottom pieces, okay? B and E, these are these pieces on the side. And we can set up, several other ratios. We can say that C over A is equal to F over D. There's so many things that we can do. But when would be a time that we would use this? Well, again, you might use this in your work, or perhaps you're going to use this in your everyday life. Um, let's say that we want to plant some. We want to put out some grass seed, and we have our house. Okay, um, we have our house here, poorly drawn, but that's okay. All right. So here's our happy little house. And we know that when the sun is at its highest, so the heat of the day, okay, we end up, I'll use a little different color over here. We end up with an area over here that is left in a shadow. And we want to know how far out do we need to go with our grass seed that, we won't be killing our grass if we're going to put grass seed that needs to be in the shade. um that's how far out we want to go with our grass seed, or perhaps we need to put down some extra fertilizer or something, okay? But we need to know what this distance is right here so that we know how far out to go. Well, we know that our house, we just happen to know that our house, let's say, I'm sorry, my drawing pad keeps messing up on me here. We know that our house is, we'll say that's 15 feet. Okay. And we also know that at this same time of day, okay, so at the same time of day, when we're standing with the sun in the same place, okay, that sun creates this shadow here. And we know that this person is 6 feet tall. And we also measure that their shadow is 8 feet long. Well, we can use this knowledge to determine how far out do we need to go with our grass seed. So we can say that 6 over 8 is equal to 15 over our unknown. And because the sun is in the same position, these create similar triangles. So now when we multiply this through, okay, we're going to get that 6x is equal to 120. And then that's going to give us that x. So we need to go out with this shade grass seed about 20 feet away from the house. Okay. All right. So now let's get into two concepts of proportion. And these concepts are going to be direct proportions and inverse proportions. Okay. So when we're talking about these two things, so in direct proportions, if thing number one increases, that means that thing number two is also going to increase. Or if thing number one is going to decrease, that means that thing number two is also going to decrease. Whereas with inverse proportions, if thing number one increases, thing number two decreases. Or if thing number one decreases, oh, I definitely can't write over that. Then thing number two will increase. So, what are some examples of direct proportions? Well, some examples would be if we know that 1 gallon of paint covers 825 square feet. Okay. Well, in this one, if we need to cover more square feet, we're going to need more paint. Um, Another example is let's say that you need or that it takes it takes a particular vehicle 42 gallons of gas to travel. We're going to say that you have a very inefficient vehicle. It takes 42 gallons of gas to travel 300 miles. Well, again, in this scenario, if you travel more miles, you're going to need more gas. Or if you have more gas, you can travel more miles. But what about inverse proportions? Well, there are some inverse proportions where we're talking about, say, like pressures. As one pressure increases, another decreases. So when we're talking about, let me write this over here. We can talk about cylinder pressure. Okay. And in an automobile, when the with regards to cylinder pressure, okay. So if the volume of gas increases, then the PSI decreases. And if the PSI increases, then the volume of gas decreases. We can also think of another example where we have different size pulleys. So, when we're talking about if we have a large pulley and a small pulley, um, they're gonna, as one moves faster, the other one's gonna move slower. Uh, but honestly, an excellent way to look at inverse proportion is something very, very something that kind of it should make sense to all of us. And this is the example of painting a room. Now, I'm not going to get into the algebra of it, okay? But let's say that one person can paint a room. Let's say it takes them 5 hours. Okay. Well, think about this. If we increase the number of people in that room, what do you think is going to happen to the time it takes to paint that room? Well, it doesn't make sense for the time to increase. If we've got 3 people or even 4 people, say we've got one person painting each wall, it's not going to take more than 5 hours to finish that room. It's going to take less than 5 hours. So as the number of people increases, the time decreases. So that's one way that we can think about inverse proportions. All right. So let's look at a couple of math examples for both of these. Okay. So first of all, let's look at a direct proportion. Okay. So in this example, we are going to look at a pulley system. and this is going to be for inverse. We'll get back to direct in a minute. Okay. So if we are looking at an inverse proportion, this is where the rule of order does not apply. So remember, we talked before with the rule of order, and this is really only for direct proportion. Okay. That if we put, say, like A on top, A needs to stay on top, B, B. Okay. This right here, this is for direct proportions. This is for when either both things are increasing or both things are decreasing. But in the case where one thing is increasing and one thing is decreasing, we need to flip the things. Okay. So the way that we're going to do that, okay, we are going to say that we are going to take and say that we've got two pulleys. So we have the speed of A, and here we have the speed of B, and this is a pulley system. Okay. So because this is an inverse proportion, we would have the diameter of B on top and the diameter of A. Okay. So let's say that pulley A hmm, sorry, I'm trying to find this. So the pulley A diameter is twice the pulley B diameter. Okay. And we are also told that when pulley A makes one turn, pulley B makes two turns. So suppose that pulley B is 16 inches in diameter. Okay. And its speed is 240 RPM. Well, in this case, that means that the pulley A would have a 32-inch diameter. Okay. And because this is an inverse proportion, we need our, like, because both of these are like the B's and these are like the A's. Okay. And like we're looking for the speed. Okay. So we want A and B to be diagonal, basically, from one another. Okay. So we have our unknown, which is the speed of A, and we have the speed of B. And then we have the diameter of B and the diameter of A. Okay. And in order to find the speed of A, we're going to do our cross multiplication just like we have. And when we do that, we get 32x is 3840, which means that x, or the speed of pulley A, is going to be 120. Okay. So I know that this looks very much like a direct proportion, but if you notice, okay, this is our speed here for A. So if you notice, the size of pulley A is bigger, but the speed is slower. So that's kind of what makes this that inverse or indirect proportion. Okay. And then just finally, last thing, let's do a direct proportion, something that most of us have done. We're going to take a trip. Okay. So here we have a direct proportion. Okay. And in this direct proportion, we know that if we are taking a trip and it takes us 2 hours to make let's say that it takes us 2 hours to make a 100-mile trip. Well, at that same speed, how long would it take us to make a 400-mile trip? So you can see this is clearly a direct proportion. Longer mileage, it's going to take us longer to get there, right? So if it takes us 2 hours to go 100 miles, how long does it take to go 400 miles? Well, that gives us our proportion. And if we travel the same speed that it took us to do the 100-mile trip, that means that to make the